Hello, this is Dr. Gardner. We're going to be talking about gases today, and as we start to look at gases, we're going to look at some units that we use when we talk about pressure of gases in systems that we will be studying. We'll also be considering some different properties of gases with respect to making predictions about volume and pressure and temperature and the numbers of moles of gases. And so we'll start looking at that. Later on in this chapter, we'll be studying some of the various gas laws, including the ideal gas law equation. So that's kind of what we're starting with in this chapter. First of all, I want you to realize we kind of live in an ocean of gases all around us. In fact, if we consider this hot air balloon, well, the hot air inside of the air balloon is going to be at a lower pressure and a higher temperature than the air outside of the balloon. This is causing buoyancy due to the hot air inside of the balloon, and because of that we're able to basically have the buoyancy of the hot air balloon draw the balloon up in the atmosphere. Okay. If we're considering these types of topics, we really want to be thinking about what types of gases are present in the atmosphere. Now, this can vary from location to location, so I'm going to give you a table here that will talk about some of the variety of different gas components in the atmosphere. After we talk about that, we'll talk about some of the properties of gases, including pressure and units of pressure. So first of all, let's consider the major component of our atmosphere. The main component of our atmosphere is about 78%, and that's going to be nitrogen gas, followed by about 21% oxygen gas. And then we have smaller percents of a variety of other gases in our atmosphere, about 1% argon. We have a little carbon dioxide. Some of the noble gases like neon and helium are in the atmosphere. We get a little methane, krypton, hydrogen gas, dinitrogen monoxide, we get carbon monoxide, xenon, we get some ozone. It's kind of interesting. Ozone at lower elevations, we tend to consider components of air pollution if it's close to the surface of the planet. However, if we start to look at ozone higher in the atmosphere, we consider it very critical for acting as kind of a natural sunscreen for the planet, meaning that it will absorb UV radiation, certain wavelengths of UV radiation, to minimize how much reaches the planet's surface and how much might affect us. So we often will talk about depletion of the ozone layer. We can also consider a variety of other gases present in the atmosphere. Water vapor can vary quite a bit, but we often are looking at nitrogen oxides like nitrogen dioxide or sulfur dioxides as components of air pollution because they can contribute to acidity in acid rain, so we will usually be worried about those a little bit. When we're considering different types of substances all around us, we can consider the major forms of matter that we will use in a chemistry classroom. We can have gases, solids, and liquids, and some of the terminology when we were converting between forms of matter that you might recall is if I take a liquid and I were to reduce its temperature until it forms a solid. If it's in a nice organized state, we might call it a crystalline solid. That process would be called freezing. If I were to add heat energy to my solid sample until it becomes a liquid, we could call that process melting, but we also refer to that as fusion. Now, if we talk about a liquid going to the gas state, we can say that's vaporization. We might also talk about taking a liquid and boiling it as it goes to the gas state. If we have a gas losing energy as it cools down, and as we're losing that energy with these changes in temperature, we can kind of relate that to a loss in kinetic energy. So my kinetic energy is going to be related to the mass of my particles and their velocity squared. So if we were to reduce my temperature of my gas phase particles, then their velocity starts to reduce. And as they start to run into one another, they'll start to act in a non-ideal fashion, and they may go from the gas state to the liquid state, and we may have a process called condensation. Now, we also, depending on the temperature and pressure conditions we're at, we may have a solid go directly to the gas state, and you've seen that with dry ice. So if you've ever had dry ice at a party, let's say, that dry ice is solid carbon dioxide, and as it warms up, it actually goes through a process called sublimation. It goes directly from the solid state to the gas state, which is why you won't see at the table under standard atmospheric pressure conditions liquid CO2 forming. So we end up with having it go directly to CO2 gas. So that's sublimation. If we were to take a gas and go directly to the solid state, we would call that deposition. Okay, so just a quick review there of my terminology as I change between states of matter. Now we're going to be focusing in this chapter on gases specifically. Okay, so when we're considering gases, we can think about the densities of different states of matter. Well, the gas state is the very lowest density of all the different states of matter, so we expect to have densities that are so small that we often report them in grams per liter, so we have liter volumes of gases before we get anywhere near gram quantities. However, if I'm talking about liquids or solids, we usually report a density in grams per milliliter or grams per centimeter cubed. Okay, many types of substances will have their lowest density always in the gas state, but then the liquid and solid state, sometimes that will vary, but most substances we'll run into would have the liquid state being slightly less dense than the solid state. However, one very notable exception is when you talk about H2O. When we're discussing water, well, the liquid state is actually a little bit more dense than the solid state because as we have water molecules form a crystalline lattice, their hydrogen bonding, their attraction between the polar molecules end up forming a nice hexagonal pattern, and so we end up with these cavities between the water molecules, and that causes a little extra spacing for the solid state, and so the density for water is actually a little bit less in the solid state as ice than it is in the liquid state. But many other substances are more dense in the solid state, so be careful there. But in all cases, though, what's quite important to realize in this chapter is gases will have the very lowest density, and you'll want to kind of keep that in mind when you're looking at our gas laws laboratory that's coming up. So my common units for density for solids and liquids, I usually report as grams per centimeter cubed or grams per milliliter, and for my gases it's usually density units of grams per liter. So be careful that you always match your units if you're doing conversions with gases, and remember you have units of liters. Now if we consider gases, well, we know their density is quite low. In fact, if I see gases bubbling through an aquarium, we can go ahead and realize that the air bubbling through an aquarium, the gases are less dense, and as the bubbles in the aquarium rise, the pressure of the water around the bubbles starts to decrease, and we see the gases expanding and as they rise, and they'll end up bubbling out of the tank to the top because of their lower density than the surrounding water. Okay, so that's something that you'll often see whenever you're bubbling gases through liquids. They'll rise up until they're above the liquid, kind of like when we talked about density columns in the past in the course. Your lower density materials end up on the top and your higher density materials end up on the bottom. So I tend to have my gases over my liquids. In fact, you'd think it was quite strange if this weren't the case, because then we would expect that if the densities weren't in that order, that we might have liquids floating up into the atmosphere, which they do not. Now, if we consider gases, they're really consisting of particles with enough kinetic energy that they've overcome their attractions between the individual particles that we have present. So for example, with H2O, we've overcome what we call intermolecular attractions between the water molecules. So we've overcome what's called hydrogen bonding between those polar water molecules at that kinetic energy, and then we end up with a large amount of space between the particles. So gases are really space hogs. They'll take up as much space as you will give them. They have a lot of space between the atoms or the particles. Now the particles for gases will consist of atoms or molecules or other species present in the gas phase. We usually don't talk about ions that frequently in the gas phase because ionic compounds have such high melting points and boiling points, but it is possible to end up with ions in the gas phase given sufficient energy. Now, if we consider how fast gas particles are moving, well, at about room temperature, if we look at an oxygen molecule, its velocity at room temperature is about 980 miles per hour. Now, that may seem kind of surprising. However, you don't always notice that oxygen gas is diffusing through a room that quickly because it does tend to run into other particles, so it's not necessarily moving 980 miles in a straight line for every hour. It's actually going to end up striking other particles and changing the direction of its motion. Okay, so when they do collide, however, if we talk about a gas acting ideally, which we expect to usually occur at higher temperatures and lower pressures, these ideal gases will tend to collide with one another, but when they do collide, we tend to, in our calculations, ignore their attraction to one another. There definitely can be attractions to the gas particles, but in the gas state of matter, those attractions are small enough that our kinetic energy of the gas particles overcome the attractions, and so they don't stick together. They tend to collide and rebound off of one another. Okay. As we have gases present that we are discussing, they will tend to expand and fill whatever container size we give them. So if I were to release a gas into a vacuum, it will continue to expand until it reaches the edges of any container that it may be within. So just remember, gases are space hogs, lots of space between them. They expand and fill up the volume of whatever container they're within. Okay, so they tend to expand. Now, if we also were to heat gases up, as we heat gases up, they will expand until we have fewer particles per volume. Now, this happens with a hot air balloon, right? You end up with a lower density gas inside because you have heated it up until the spaces between the gas particles of the air inside of the hot air balloon are further apart, and we end up with having a lower density of the hot air versus cool air. So that's something that's nice to remember. If you compare two identical gas systems, the higher temperature system should have the lower density, and the lower temperature system should have the higher density, assuming that we've given it a chance to potentially expand. So let's say we take a cool gas, we heat it up, we can have that cool gas heating up until we end up in that same volume having maybe only 2 gas particles of diatomic oxygen gas shown in this picture versus having 4. So that would cause us to have half the mass per volume. So the density has then decreased. Okay. It's all because that increasing kinetic energy makes the particles move faster, they collide harder with one another, and they tend to spread out and take up more space if they're given the opportunity. Okay. So it's the warm gas that has the highest density out of the two. This is exactly why that hot air balloon will rise, and so if we consider the air outside of a hot air balloon with the lower temperature gases, the higher temperature gases from the air being heated that's within the hot air balloon have additional space, and so the density is less. And just as we'd expect with any density column, our sample of substances with the lower densities tend to rise, and this can cause enough buoyancy in the surrounding atmosphere with the cooler gases surrounding the hot air balloon that it can provide lift for the balloon itself and the basket under the balloon potentially with its occupants. Okay. Now let's consider how pressures relate to gases. If we're looking at pressures, well, pressure really is a force being exerted from the collision of the gas particles on the surfaces of its container. And so it's these forces being exerted over an area. So really that's how we can relate to pressure. It's force over area. Okay. Now changes in pressures can affect the properties of gases that we'll be looking at in this chapter. And we're probably pretty familiar with that. If we go ahead and increase the pressure in our tires, we end up with more collisions on the surfaces of the tire, which can go ahead and inflate the tire. This will also relate to temperature. Okay, so we'll be thinking about temperature in a minute. But let's consider as we add more moles of gas or more molecules of gas into the tire, it tends to expand from the increasing volume of gas. We end up with having more collisions on the surfaces, which increase the pressure inside the tire. This will be related to the pressure outside the tire. We will try to have a similar amount of pressure inside and outside of the tire, while we may be in that simple discussion ignoring what's happening with respect to any resistances of the rubber expanding of the tire itself. But let's think about what's happening to the density. As I put more gas into the same volume of the tire, well, the density of the gas must start to increase because I'm going to have more gas particles per volume. Okay, so I expect a slight increase in the density. Now let's consider about how a balloon would inflate. As I put gases into a balloon, we're going to have collisions due to the gas particles on the surfaces on the interior of the balloon that end up basically relating to the pressure outside of the balloon. So the balloon will continue to expand until the gases inside the balloon, which had an increased pressure as I first put them into the balloon, it will expand until they match the pressure outside of the balloon and as well as the resistance to the rubber of the balloon expanding here. So really we're thinking about all these gas particles inside the balloon colliding with the surfaces of their container. Okay, that's going to be important for thinking about pressure because remember I said pressure is going to be force over area. So it's the force applied due to the collision of the gas particles on the surfaces of its container divided by the area of the container. Okay, so if the balloon expands, we can go ahead and match the pressure of the gases inside the balloon versus the outside of the balloon by having the area of the container increasing with the expanding balloon. Okay, so let's think about pressures with respect to when you're dealing with, let's say, a thumbtack or a nail. If we're thinking about where the pressure is the greatest, If you're holding a thumbtack between your fingers, well, the pressure is the greatest where you have the smallest area. So we're applying the same force to both the thumb and the index finger in this picture, but since I have a smaller area over the tip of the thumbtack, that's where we're applying the greatest pressure. The same thing with a nail. If I'm trying to drive a nail into wood, I want the greatest pressure on the tip of the nail going into the wood itself. So the smaller area on that tip of that nail with respect to the force being applied will cause a greater pressure, which drives the nail into the wood. If I had the nail reversed, we'd end up with the greater pressure being exerted against the hammer, and we wouldn't be very successful at driving that nail into the wood itself. So we're kind of thinking about that. With gases, however, instead of looking at a nail or a thumbtack, we're looking at the forces of the gas particles as they're colliding with a surface area. Okay, so let's consider two different molecular viewpoint pictures of gases inside of a container, and let's think about which would have the greater pressure. If we look at gas A or gas B sample, if we're trying to decide which has the greater pressure, if we're assuming they're at the same temperature, the average kinetic energy, the energy related to the motion of the particles, are the same. So they're moving on average the same velocities. Okay, so each gas particle, when it strikes a surface, would be applying the same amount of force, but if I have more gas particles present in a volume, we would end up with having greater pressure at this temperature because we would end up with exerting a greater force from more collisions on the surfaces of the container, and we would have the same area we're assuming in this container, so the greatest pressure would be that sample which has the most moles of gas within that same volume container. Okay, so sample A has the fewest particles, it has the lowest pressure that we're dealing with at this same temperature, whereas gas B sample has the most particles, so it would have the greatest pressure with respect to the sample that we're looking at. Now let's consider if we were to take a metal can and exert a vacuum on it. By exerting a vacuum, what I mean is we basically have a low pressure region that we're producing inside of the can itself by drawing the gases out. We could use a rotary vacuum pump or other types of vacuum pumps, but a rotary vacuum pump is the standard one we would look at. As I draw the gases out of the interior of the can, though, the atmospheric pressure outside is being maintained. So we have less and less pressure being exerted on the inside surfaces of the can until the surrounding atmospheric pressure, which is greater than that within the can as I'm producing a vacuum of that low pressure region, will cause the can to crush. Now, if we're looking at this at the molecular level, we can think about the gases outside of the can that we're looking at having more particles per volume at this temperature than the gases inside of the can. So I have fewer particles per volume. What's happening then is I have these particles striking the surface on the outside of the can, and I have the particles within the can striking the surfaces on the inside of the can. With that reduced pressure inside of the can, we're not matching these two pressures. And so as I draw that vacuum and I have fewer and fewer particles inside of the can striking its interior surfaces, the surrounding atmosphere particles will strike the outside of the can until it crushes. Okay, so that's what's happening in this situation. There's a lot of really interesting YouTube videos if you look them up with respect to the atmosphere crushing soda pop cans, or you can look at 55-gallon drums, or you can even see this occurring with respect to videos of low pressure systems in basically tanks for different cars on trains. So you can actually see the atmosphere crushing those types of containers. Okay, so if I'm talking about pressure, we want to use some different units for pressure. In the US, we often talk about our pressure in pounds per square inch. Okay, and you might be used to that when you're inflating, let's say, a bicycle tire. However, in a chemistry classroom, we'll often be talking about inches of mercury that we might use in a barometer in the laboratory, or we might be talking about millimeters of mercury. In fact, millimeters of mercury will be quite common, or we might talk about torr or atmospheres. Now let's consider what an atmosphere is. One atmosphere is the pressure that we expect the atmosphere to be exerting at about sea level, okay, under what we call standard state conditions. So the standard temperature and pressure conditions would be a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. Okay, so if we're looking at those situations, we should maybe know some of our unit conversions. So 1 atmosphere would support a column of mercury if I have a vacuum being applied above the column of mercury and I have atmospheric pressure pushing down on the surface of a barometer's pool of mercury. It would support a column of mercury that would be 760 millimeters of mercury high. We can also relate that to torr, so 760 torr. This is related to the Italian physicist Torricelli, who discovered the principle of the barometer in 1644. Okay, so if we really look at this, 1 atmosphere is 760 millimeters of mercury, 1 atmosphere is 760 torr, so there's going to be 1 torr for every millimeter of mercury. We can also realize that 1 atmosphere can relate it to a pressure unit of pascals, so 1 atmosphere is 101,325 pascals, or you might hear it referred to as 101.325 kilopascals. So if you hear kilopascals, that's commonly used because our Pascal unit is so much smaller than the atmosphere unit. If I'm also talking about 1 atmosphere, that's equal to 14.7 psi. Okay, so I want you to be able to do some of these types of conversions between different units of pressure. So let's consider if we have gas pressure in pascals. So I have a gas that has a pressure of 8.25 times 10 to the 4th pascals, and I'd like to know what this pressure is expressed in units of atmospheres and torr. So I've given you some reference conversion factors that we can use, and as we're setting this up then, the conversion factor I would like to use first is that 1 atmosphere is equal to 101,325 pascals. So if I set up that conversion factor, my 8.25 times 10 to the 4th pascals is going to be divided by the 101,325 pascals for every 1 atmosphere. So I'd end up with converting this to atmospheres. It would be 8.14 times 10 to the negative 1 atmospheres, or basically 0.814 atmospheres. Okay, so this makes sense. This could be atmospheric pressure you could be dealing with at above sea level when you're dealing with less than 1 atmosphere of pressure. If we want to convert that to millimeters of mercury, well, I know 1 atmosphere is equal to 760 torr. Okay, so I can realize 8.14 times 10 to the negative 1 atmospheres can be converted to torr by multiplying by 760 torr for every 1 atmosphere. So I'm going to end up with 619 torr, or in scientific notation, 6.19 times 10 to the 2nd torr. So anything below 760 torr would be less than 1 atmosphere. Okay, so this is a very reasonable answer. Now let's consider some of the factors that can affect the properties of gases that we were talking about them. Now that we know how to use units of pressure and do some simple conversions with them, which is you should be practicing in your homework, we can start to look at how we can describe gases. We often will want to talk about the volumes of gases. Now when I measure the volumes of gases, we will use units of liters quite commonly. However, you might measure some gas volumes in the laboratory in milliliters, but realize in my calculations I will usually want to convert those milliliters to liters. So make sure you're writing all your units down, because if you forget to convert from milliliters to liters, you may have some conversion problems, and if you haven't written your units down, you may not cancel units properly and be off by a factor of 1,000 if you haven't converted to liters. Now when I deal with pressures, well, I've shown you a variety of pressure units, but basically when I'm dealing with pressures, I would like to work in atmospheres in the laboratory most frequently. We're going to see these units that I'm picking for these different properties of gases will work very nicely with a gas law constant R, which has been determined with these specific units. Now my temperature in the laboratories, even though I tend to measure my temperature in degrees Celsius in the laboratory, I want to convert it to Kelvin in order to use my ideal gas law equation in this chapter. So when we're dealing with temperatures, add 273 to your degrees Celsius to convert it to Kelvin before you use it in your calculations in the ideal gas law equation. Okay, so we're looking at volume, pressure, and temperature with dealing with gases. I'm also interested in how much gas do I have? How many particles do I have in the gas phase? So we'll measure the number of particles in the gas phase we have between molecules or atoms or any gas particles we might be looking at. We're going to measure that in moles, and I'll usually use the lowercase n as the variable to represent moles in this chapter. Okay. Now if I'm treating these types of situations as an ideal gas, well, we want to see how those gases would behave according to linear relationships frequently. Okay, so we'll be looking at that with graphing some of these properties coming up in the next discussion. Now as I start looking at volume and pressure, realize that as I have a lower pressure inside of a container, its volume will tend to increase. So if I have a balloon rising in the atmosphere, the surrounding pressure of the gases outside of the balloon as it goes up starts to decrease. This causes the balloon to expand to try to match the pressure inside and outside of the balloon. And so potentially that balloon continue expanding until potentially it could rupture. So we expect that as I have a weather balloon rising in the atmosphere, its volume would increase because of the decreasing surrounding pressure of the atmosphere. The reason bubbles rise in water is because they're rising from a greater pressure to a lower pressure, and they will they will increase in size with that decreasing pressure in their surroundings, and so we'll actually see the bubbles of gas expanding. Okay, you may have seen that when you've been doing cooking and you end up with water vapor in your pots or pans. You may see the bubbles of the gas expanding as they go up. It may not be as pronounced in that case because you may have a temperature gradient in the water in your pot or pan, though. Now, we can deal with pressure and volumes in different containers, but it's quite useful when we're looking at these to consider, let's say, a syringe barrel, or we can think about having a piston in a car. In those types of situations, if I take a volume of a gas with a larger volume inside of our piston, if I were to decrease the volume of the gas by pushing the piston down, we would see that the volume of the gas decreases, but the number of moles of gas is still the same, so I have more particles per volume. Since I have more particles per volume, if I were to maintain the temperature of this situation here, so I'm still at the same temperature, okay, so I have the same amount of gas, same number of moles of gas at the same temperature. Then as I decrease my volume, then I expect the pressure to go up because now I have more collisions per surface area. So that will result in an increased pressure of those particles striking the surfaces inside of the cylinder. Okay, now we can relate this to a law called Boyle's law. We can say that pressure is inversely related to volume. So as I have decreasing volumes, pressure is going up. If I were to increase my volume, pressure would go down. Now we can relate this pressure and volume to a constant. Okay, if I want to look at that, then I can say pressure is equal to a constant times 1 over volume, inversely related again. Or I can say that volume is related to 1 over pressure, the inverse of pressure. Now what I can do here is relate this to an equation that has changing pressure and volume conditions. I can say that pressure initial times volume initial would be equal to a pressure final times volume final. If I do this, I'm looking at two situations where I have the constant related to the initial pressure and volume and the constant related to the final pressure and volume, so the constant has canceled out as I related these two equations. Now I will show you later how to relate these types of laws, like Boyle's law, to an overall ideal gas law equation. So we'll be coming back to that. But let's work a simple problem relating to changing conditions of pressure and volume using Boyle's law. So if I have changing volumes and pressures, but no changing temperature, so I'm holding temperature constant, and I'm holding the number of moles of gas constant, I can use this equation to relate a gas sample. So let's consider if we have a pressure of a 2-liter sample of gas, and we're decreasing that pressure from 1.2 atmospheres to 0.25 atmospheres under the constant temperature and constant number of moles. What would be the new volume we're dealing with? Okay, so since I'm holding temperature and numbers of moles constant, you won't see a variable relating to temperature or a variable relating to numbers of moles because they were identical before and after this process. So I can say that the pressure initial times the volume initial, that's my pressure 1 and my volume 1, is equal to my pressure final times my volume final, that's my pressure 2 and my volume 2. If we're looking at that situation here, I can often find it quite useful to set up my calculation by relating to the variables that I have. Okay, so I might want to define all the variables that we're looking at right now. Okay, so what I'm going to go ahead and do here is I'm going to say, okay, what is my pressure 1? Whoops. Let me grab my pen here. So I say, what is my pressure 1? Pressure 1 initially is going to be the 1.2 atmospheres. And I can say that my volume 1 was equal to 2.0 liters. And I can go ahead and say that my pressure 2 is equal to 0.25 atmospheres. So what I'm solving for then is my volume 2, or my final volume. So I need to algebraically here, so this is the unknown variable, this is the unknown variable, volume 2. So what I need to do is algebraically solve for V2. So I'm going to divide both sides by my final pressure, P2, of my equation. And we'll see in that situation that we'll isolate volume 2. Volume 2 will be equal to my pressure 1 times my volume 1 divided by my pressure 2. Okay, so my pressure 1 would be 1.2 atmospheres. My volume 1 was my 2.0 liters. And my pressure 2 that I'm dividing by was 0.25 atmospheres. So since I know that volume and pressure is inversely related, if I decrease my pressure, I expected my volume to have increased. And in fact, if I calculate this, we could find that we would have the 1.2 atmospheres times 2 liters and divided by 0.25 atmospheres. We're going to end up with a final volume here under this situation of 9.6 liters. Okay, so after this discussion today, I'd like you to go ahead and start working on your homework problems relating to pressure conversions, and then some work on your homework problems related to Boyle's law calculations. In our next video discussion, we'll be looking at Avogadro's law as well as Charles' law with respect to the gas laws, and then we'll start to combine our gas laws to look at the ideal gas law equation. So that's what's coming up here in our next video discussion. Okay, good luck everybody.